Last time we talked about the basic ideas of string theory, and the end point was seeing how string theory accounted for various different kinds of apparently elementary particles. That in fact what one thinks of as elementary particles in quantum field theory, according to string theory, are just strings in different excitation modes. And so that determines their masses, and when you have the states of a particular mass, you can organize them into different subspaces of particles of different spins. We were only talking about the bosonic string theory, but that's enough to see that there's a massless spin 2 particle, which is the characteristic of the graviton, the quantum of the gravitational field, if it is indeed quantized. And tomorrow we'll explore what comes from that. We also saw from the open string there was a state that looks like a photon, just a massless spin 1 particle. And so those are two nice sort of physical looking particles, and then there are others. So that got us to the first point, the first big idea in string theory about concerning the nature of matter, that we can find string states that correspond to quanta of quantum fields. As I said at the beginning, we're also interested in the status of space and space-time in string theory, particularly space in the lecture today, and that is what we're going to talk about today. I'm going to put to one side the stringy quanta that we've discussed, and think about some of the implications of string theory for the nature of space. And then we'll return to putting them together in the lecture tomorrow. Okay, so we're going to be thinking of a system that's much like the quantum, we're going to be thinking of the quantum string that we developed yesterday. We're actually going to model it in a slightly simpler way to bring out and discuss an important and rather striking symmetry that exists in string theory that goes by the name of T-duality. So, bearing in mind what we learned yesterday about the nature of string theory, imagine the same kind of system that we've been talking about, but we want to consider strings that, or a string will be enough for our purposes here, but strings that live not in a space-time that's infinite in extent, but that has a spatial dimension that's curled up, that is a closed spatial dimension, that has the topology of the circle. So space-time might be in some sense cylindrical, with one rolled up dimension, and all the others going off to infinity. So the surface I've drawn here has, it's a two-dimensional surface. It has one circular dimension and one infinite dimension. Or we could have a torus if we imagine the ends of this joined back up. And of course, we're talking in bosonic string theory in 26 dimensions and 5 spatial dimensions. So those are the kinds of objects that we're interested in. But we are going to focus on just that one closed dimension. Whatever's going on in the big other space, if the other dimensions are closed, the same things will apply. Okay, so let's think about the state of how to describe the state of such a string. And we'll start in the classical picture. So I've got a string living in such a space, and at any time, or at an initial time, it has a location, and then it also, to describe its state, its motion is also important, its velocity, or we're going to change to its momentum, which encodes the velocity of the string. But to say what the state of the string is like, it's also obviously going to be relevant to say how many times it's wound around this closed dimension. Okay, if it's wound round twice, it has to be stretched twice as long, and that's a different state for the string because it has tension. If it goes around once, it has one amount of potential energy due to that. If it's wrapped around twice, it has to have more potential energy because it's wrapped around twice. So, clearly, for a classical string, it doesn't have any interactions. That's not such an interesting number like the position and the momentum because it doesn't change over time. But the point is, when we go to the quantum system, this is no longer a constant of the system. It's going to be a dynamical quantity like position and momentum. Okay. So to proceed on this, what's going to be relevant here is finding the Hamiltonian. So the system we're going to approach as a pretty straightforward quantum mechanical system. And what we need is the Hamiltonian. So yesterday we talked about the action that we used for the string was the Nambu-Goto action, which is just proportional to the world, as I said, to the space-time area of the world sheet. I also mentioned there is an equivalent action called the Polyakov action or the sigma action, which I'm going to give you now, and at the classical level is demonstrably equivalent. So the action, this is just a different way, it's just a different formulation of the action. It's the same action, but when it's written in this form, it's called the Polyakov action. So it's the same as before. We have to integrate over the world sheet variables. This is the time coordinate on the world sheet, and this is the space coordinate on the world sheet. Again, we have the tension, but this is not the most general form of the Polyakov action, but it's the one we'll be looking at today and tomorrow. What we've done here is already actually pick a particular special set of coordinates on the strip, a special set of coordinates on the world sheet. Sigma and tau, some particular choice has been made, which will simplify the expression. So, at the heart of the action then, remember this X field is, encodes the position of the string in space-time, how it's embedded. The X's here are the X mu sigma tau. You give me a point on the world sheet. You give me its sigma and tau coordinates. This function then gives back a coordinate for each of the space-time dimensions. The squaring here, these are 4 vectors or d plus 1 dimensional space-time vectors. So the squaring here refers to taking their dot product with respect to the Minkowski metric. So the time components get multiplied together and pick up a minus sign, and the other components just get multiplied together and you add them up. So these are just vector squaring, taking the dot product with itself in Minkowski space-time. The dot on the X here refers to a single derivative with respect to the tau coordinate on the string, and the prime, can't see it too clearly there, is a derivative with respect to sigma. I've written it this way with both the integrals separated out to remind you that the action is the integral of the Lagrangian along the trajectory. So this part in parentheses is the Lagrangian, and then it's integrated. Then there's a standard formula to go between the Lagrangian and the Hamiltonian. So simple coordinates, but it's easy to sort of see. This is a time derivative squared term, so it's a kinetic energy. This then must be some kind of potential energy. The Lagrangian is the difference between the kinetic and the potential energy. The Hamiltonian is the sum of the kinetic and the potential energy. If you work out what the actual canonical momentum is and plug it in, use this formula. Again, this is the Hamiltonian, and we interpret this. Okay, there's no time derivative because it's the energy at a particular time, and it looks something pretty reasonable. It looks like a kinetic energy term plus a potential energy term. Okay, so we have our Hamiltonian. If you remember last time, we had a sort of general solution for our equations of motion that had a center of mass term plus a velocity term and then vibration terms. Well, we're going to ignore the vibrations just to keep things simple. I'll point out where they can come back in again in a bit. But if you think about, so imagine a string wrapped around. The position is going to depend, there's going to be a term that is something like the velocity times the time, because that's going to be the time dependence. I'm just imagining it's not vibrating, it's just moving continuously. And as I go around the circle, as sigma, actually in this case I'm going to let it vary between sort of 0 and 2 pi as I go right the way around the string. The x-coordinate is going around the cylinder. And so, okay, so if sigma is 0, we expect, so ignore the time dependence, just imagine this term is 0. We're going to set the point of the string that's at sigma equals 0 to be at the 0 of space. X will be 0. And it's going to increase, it's going to be stretched evenly. So as I go around the string, equal angles around the string correspond to equal angles in space. So by the time I've gone halfway around the string and sigma is equal to pi, I've gone, let W be 1 for the once wound. When I've gone pi around, I've gone pi r around space. So this is just going to be translate distance around the string into distance around the space. W is the winding number, because if the string's wound twice, I have to go all the way around space twice to go once around the string. And so this is going to bring me around, this is going to take care of the fact that both the strings wound around once, both 0 and pi, halfway around the string, are actually the same place in space. Halfway around the string is once around space. I'll leave this so you can sort of convince yourself this is going to be the right way to embed the string in space if there's no vibrations. One would expect here a sort of v tau term. It's more convenient to write it in terms of the momentum. So p is just like is characterizing the motion through space. Tau is acting like time on the world sheet. We've picked units in which c and h bar are equal to 1, and those are units then in which momentum and distance have reciprocal units. This is a distance, so this term has to be a distance in units. So p is like 1 over a distance, so I need a distance squared here to make sure this whole term ends up as a distance. Okay, that's why we have to have some length here. This is called the characteristic string length, and we have to have some constant squared to make this into a proper, to make this term have the right units, to make it be a term that has the units of length. Tau looks like time, so you might think that there's a sort of seconds involved in the units here as well. But remember, this isn't space-time time, this is just a parameter on the world sheet, so this doesn't really have units. The point about this L squared then is P has units of inverse length. To make this really a length, which it has to be because it's a distance on this side, I have to have some new constant length term to make the units work out. So L sub s, it's called, as I said, characteristic string length, and it is ultimately the only parameter that you have to put into string theory. It's actually, you may think we've also put in tension here. This is a parameter in the theory as well, but it turns out these two things are related quite simply. So we have the string length, and a typical sort of scale like this is, it could be equal to the Planck length or a little bigger than the Planck length. As I said, that also sets the tension, but this is a characteristic length scale in the theory. One of the things people advertise about string theory is instead of having all the independent constants of the standard model, it's just one, and it's this one. And at this point it enters because this has to be a length. Okay, I digress a little bit there, and so we've done the work we need to. We got the Hamiltonian out of the Polyakov action. We've specified a particular solution for the string to illustrate things. Plug it in, and you'll see this is what the Hamiltonian is. Take the derivatives, take the squares, you'll get a 2 pi from doing this sigma integral. This is the upshot of what we've done so far. Okay? And so classically, there's a sort of asymmetry between the two terms that are involved. P is a dynamical term that can change and take on continuous values. W is a fixed term classically, but only takes on discrete values. But if you start to think about it, things are going to change for both of these when we go to quantum mechanics. Let's see. So keep the same system in mind. A string that's wrapped around a cylindrical dimension, and apply quantum mechanics. Well, where we have momentum, there's these two, so we'll quantize the momentum first. Momentum, and we'll think about the momentum eigenstates. They're of course plane waves, as you see here. But we're on a cylinder, so these wave functions are periodic. Every time I go once around the cylinder, the wave function has to take on the same value. The wave function has to be continuous, so it just has to take on the same value at 0 and at 2 pi r. This problem of periodic boundary conditions for plane waves is a pretty standard one in quantum mechanics. Okay. The periodic boundary, given the form of the wave of the momentum eigenstates, given the periodicity, we have to identify these two things, and of course the upshot is that P has to be some whole number multiple of 1 over r. That way we get because of the boundary conditions, and of course that is to say P is quantized in these amounts. We can write it in terms of n over r, plus where n is some whole number, and n then is the wave number. So we can substitute that back into take the Hamiltonian, and in place of the L squared P over R all squared, we'll now substitute, sorry, this was a P, yeah, P not an R, P over R. If you compare with the Hamiltonian before, where we had P, we now write n over R. That's what we've just found out for the energy eigenstates. So, at the quantum level in the first place, now the momentum and winding terms, the kinetic and potential terms, look the same. They come in discrete units. There is now a parallel between momentum and winding. They come in discrete units. But more than that, what we're really interested in string theory is one in which strings can interact. In particular, that's going to mean, I'll draw you an open string rather than a closed string because they're quicker to draw. I can have a string coming along and, for instance, at a certain time it can split into two. Well, we can also get a process in that case. So the ends of, if you have two ends of strings, they can come apart and they can join together. That makes it possible, I think I've drawn a picture, this is supposed to be a picture here, where at the bottom I have a doubly wrapped string. If you have a doubly wrapped string that splits and joins in two places, you end up with two singly wrapped strings. That's a transition that you want to be able to have in a quantum theory of strings. So that I should have brought an elastic band, you sort of imagine it wrapped around twice, and it breaks, but at a certain point it snaps into two places, and you end up with two strings both wrapped around once. That's a transition that's supposed to be able, that's at the heart of string theory, that is supposed to be able to happen. So W, the winding number, the number of times wound around, is not going to be a C number, as you would think in a classical case. It's not a constant. It's a dynamical quantity, and formally, and indeed conceptually, and that's in a sense the point of everything we're going to talk about today, or a lot of what we're going to talk about today, a dynamical quantity on a footing with X or beta P. Clearly it appears, W appears with N in the Hamiltonian, or in the energy eigenstates, so it's a quantity that's akin to momentum. It's like a second momentum for this system, once we think of winding as dynamical. Okay, but still we can look to the classical picture, and it's clear that winding can only come in whole numbers, can only be wound a whole number of times around. Those have to be the eigenvalues. We can have a superposition of different numbers of winding, but the eigenvalues are going to be whole numbers, and for the same reasons in the momentum case, if you want a quantity to have whole number eigenvalues, the way to do that is to have its eigenstates be plane waves wrapped around a cylinder, so that there are periodic boundary conditions. The periodic boundary conditions, as we just saw, lead to this kind of discrete spectrum, even levels. Okay, so we're just going to apply the same reasoning as to momentum. Momentum, we sort of took the wave functions and imposed the boundary conditions, and saw we got the whole number eigenvalues. This way we're reasoning the other way. We want the whole number eigenvalues, so we're going to have plane wave eigenstates, and we're going to wrap it around a cylinder. But what we notice is, looking over here, this is the momentum term, remember, when we had a cylinder of radius r, we ended up with a term, we ended up with eigenvalues proportional to 1 over r. Over here, we want this term, these energy eigenvalues, to be proportional to r. So we're going to need a cylinder whose radius is 1 over r. What shows up in the energy eigenstates, or in the eigenstates, the eigenvalues, is 1 over the radius of the cylinder. So if I want eigenvalues that are proportional to 1 over r, I have a cylinder radius r. If I want eigenvalues that are directly proportional to r, I need a cylinder that has radius 1 over r. Okay, and then you can see the math works out. Again, we have periodicity. Here the radius is 1 over this quantity r. So the periodicity tells us that when I go from the value of the wave function at 0 and 2 pi over r has to agree, plug in the wave functions, and then you can see that with the eigenvalues have to be just directly proportional to r. And we will then interpret this number, this eigenvalue, this whole number that goes with r, as the winding number. Okay? So, the treatment is exactly parallel to that of momentum and quantized momentum, except we have to have a reciprocal radius. So this is sort of weird now. This is a wave function that sort of lives in ordinary space. We've been led by this reasoning to postulate another dimension, which has radius r, for this wave function to live in. So it can't be the same space, because this one has radius r and this has radius 1 over r. Once we want to quantize the string and treat the wave winding number as a dynamical quantity, like momentum, as looking at this, the Hamiltonian, and thinking about things quantum mechanically we should do, we've been led to discover another direction in space, a new dimension. For every closed dimension of actual space, there is a second dimension in which the corresponding winding wave function lives. And this is a quotation from an article in Physics Today that Ed Witten wrote about this. He literally describes this as another direction peculiar to string theory. So I should say, there we go. Yeah, okay. Okay, so I've just recapitulated, over here I've just recapitulated the energy formula, and, okay, I've drawn a picture of the situation. So we started with space that the string is living in and wound around, radius r, and there's some wave function in there representing its momentum. And in particular, if it's a plane wave around there, we have a state of definite momentum, an eigenstate of momentum. Correspondingly for winding, there's another space of radius, reciprocal radius 1 over r, and another wave function representing the state of its winding. Another wave function representing the state of its winding. And if it's a whole number of if it's an eigenstate of winding, then it's a plane wave living around there. Just to be clear, this is the space that we were, in the classical picture, thinking of the string as actually being wound around and stretched around. It's important to realize this is where the wave function describing the quantum winding lives. The string's not actually wound around here. You should give that picture up. If the string's wound around anything, it's this space. But the state we use to describe the winding lives in the second space, the wave function to describe the winding. So keep the thought of the string being wound around something separate from the state, the quantum state, the wave function that's describing that winding. Those are not the same thing in this picture. Okay. I should say, in fact, the picture we're looking at is in some sense an approximation to what really goes on in T-duality and in the string. But the features of this description are accurate enough for our purposes, and indeed the duality, the symmetry we're going to talk about, does not depend on this picture. It's an exact symmetry that works just the way that I'm describing. It's just this is a really nice way for thinking about this conceptually, as we'll see. Okay, and now we look at the energy, we look at this formula, and it becomes quite apparent that the energy is unchanged if r, the radius of the space, the string, the original space, is transforms to L squared over r, basically goes to its reciprocal, and for eigenstates it's a eigenstate of momentum and an eigenstate of winding. I change the wave number with the winding number. You can just easily look up here and see that transformation, this energy is a symmetry of that transformation. That's just a mathematical fact. By the way, okay, okay. So that's kind of interesting. It's sort of as if, looking at this picture, if this space had radius 1 over r, and this one had radius r, and I'd had a wave function over here of, on the now small space, a momentum with wave number n, and on the big space over here, a winding number, a wave number w over here on a small space and a winding number n here on a big space, that would not have changed the energy. Okay? That's what that symmetry does. It takes the reciprocal of each of these spaces and exchanges the winding and wave numbers. But let's think about it sort of more generally. Up here we're thinking about eigenstates of energy, so eigenstates of momentum and eigenstates of winding. More generally, we'll start with a theory with a space of radius r, and I've chosen that to be the large number. And the let's say, just some wave function living in that space, representing, well, it's a position wave function, but that's also describing the momentum. And in the second smaller space, a different wave function, which may or may not be an eigenstate, describing the winding. The general version of this symmetry takes the reciprocal of each space, so where the space in which, so I'm just going to call it space, the space in which the string lives, or the space in which the string lives, takes on radius 1 over r. Simultaneously, the space in which the winding wave function lives, which starts off small, so this is in the first theory, take the reciprocal of 1 over r, and I get r, so it becomes big, and simultaneously, I'm going to take the wave function from the winding wave function, and now treat that as the position wave function on the small space, and take the position wave function and now treat it as the winding wave function. Okay. Take the reciprocal radii and exchange the wave functions. So there's a mistake here. This should be a y here. Okay. I'm always going to say the space over here, the coordinate is x, and the one over here is y. So what this reflects is taking the reciprocal radii and exchanging the wave functions. Okay. So formally that looks pretty kind of trivial. These pictures look pretty similar here. I've sort of moved this down to here and this one over to here. So you can see why formally there's going to be a symmetry here. But remember how these are supposed to be interpreted. The space on this side is the space in which the string lives, and insofar as it makes sense, and we were thinking about it this way, this is the space in which the string is wound around. In this case, the string, if wound at all, is wound around a really big space, and in this one, if wound at all, it's wound around a really small space. Okay. What's going on this side refers to the momentum of the string, and what goes on this side refers to the winding of the string. This says one thing about the momentum and winding. This says something completely different about the winding and momentum. Something that's wound, however it's wound in this case, it's wound in a very different way in this case. Whatever its momentum is in this case, its momentum is very different in this case. Its momentum is determined by its spatial wave function psi in this case, in a big space, and by the spatial wave function phi in this small space in this case. Formally, you can see why it's very easy to see why there's a symmetry here. Because in both cases they have the same form of the wave function on the same sized space, but they are not, at least the way we've set things up to this point, the same situation at all. One, for instance, might say there's 3 units of momentum and it's wound twice, whereas this one says there's 2 units of momentum and it's wound 3 times, and around different sized spaces. Okay. That all has to be taken in the quantum sense, but they're physically different the way we've set things up. Okay. That's pretty good. This symmetry, so for the end, we started with the energy, but the same thing goes for any observables that you can come up with for this system. You have to systematically rearrange the observables so that the observables from this space go over to this space, and the observables from here go to here, but there's a systematic mapping between the two systems which preserves every value of every expectation value of every observable in the system. And so that's demonstrable, that is the nature of the duality. To help you think this through, I'm not quite sure. Okay, good. It might be helpful to think about a sort of a simpler duality, which is a simple harmonic oscillator duality, which actually exists both, unlike the string one, we have to go to quantum mechanics, because otherwise this wave winding space call this W space for winding space, doesn't exist. For the simple harmonic oscillator, I don't have to go to quantum mechanics to see it. Here's the Hamiltonian. You can see, again, it's symmetric under... so I'm imagining this my system here. I've set it up so that it's a little mass bobbing back and forth on a spring. Right. So M is the mass of the spring, not up and down, but back and forth. M is the mass of the string. K is the spring constant. It's just a nice little classical system. Nothing weird happening here. And so, right, I just have a kinetic energy term and a potential energy term, sort of in the normal way. But it's clear. This is symmetric if I change the mass to 1 over k and k to 1 over m, and I exchange position and momentum, picking up a minus sign on 1. You see that's a symmetry of this. So what does that mean? Thinking about it classically or quantum mechanically. So imagine you have two such simple harmonic oscillators, okay, that are related. One has mass m and spring constant k, the other has mass 1 over k and spring constant 1 over m. And, I don't know, you go out of the room and I set them both going and I get a table for each one and I, at different times, write down the momentum and position and how they're correlated over time. And then you come back in the room, and I do that for each of them. And you come back in the room, and I show you these tables of correlated quantities. But I forget to write down which one the table came from, and I forget to put at the top of the column which column is momentum and which column is position. Well, I do it in this funny way. One of them is actually minus position. That's the way I write it down. But I just give you these two tables, and I ask you, which one corresponded to which of the oscillators? From the patterns of correlations between these quantities, there's nothing you can do to tell. If of this pattern of data, correlations between x and p work for m over k, then the same set of numbers that I've written down in this other way will work for the other oscillator. There's nothing you can tell just by looking at those values to say which table belongs to which oscillator. That's the nature of the symmetry here, and it's the same in the case of the T-duality. That's the kind of way to think about what's going on. If I give you any sort of set of observables and how they're correlated, there's an interpretation for which this makes sense, and there's an interpretation for which this makes sense. There's nothing you can tell by looking at the values of those observables to tell you which one is which. Of course, in the simple harmonic oscillator case, you think, okay, I can tell them apart. Okay, I can't tell them apart from the tables, but at least I can dismantle the things and I can just weigh the mass of the bob in each case, and that way I can tell which one, I can distinguish them in that way. So, and that's right. But it's not clear there's anything in string theory that sort of corresponds to pulling the thing apart and seeing what the mass is, or seeing what the spring constant is. It's supposed to be a theory of the whole universe, and what is the experiment that's going to tell you, which one of these two duals? It looks like what you should want to do is, okay, what we need to do obviously is measure the radius of space, and that will tell us which of the duals is right.